Okay, in this video I'm going to talk about how you can use Kirchoff's laws to predict the voltage and current at different points in a series circuit. I'm going to make this a 9-volt battery powering this circuit, and we can see it's series because there's only one pathway through the circuit. The current has to go through the 5, then the 10, then the 15 ohm resistor, and back to the battery. There's only one way to go. That's what makes it series. So the way we approach this is we start with Kirchoff's voltage law. We're going to start at the point right here, and we're going to see that we go up the voltage of the battery and down the voltage of these 3 resistors. Now to keep everything straight, I'm going to call this one resistor 1, this one resistor 2, and this one resistor 3. So when I use Kirchoff's voltage law, I'm going to say that I have the 9 volts that I went up through the battery, and then I'm going to go down the voltage associated with resistor 1, so this will be V1. Then the voltage associated with resistor 2, this will be V2. And then the voltage associated with resistor 3, and this is V3. So I don't know what V1, V2, and V3 are separately, but I know they all have to add to 9 volts so that I go up the same amount that I come down to get back to the point where I started. The secondary thing that I know, because it is a series circuit, is that the current at all locations must be the same. Those electrons don't have any different pathways to go down, so the amount flowing around in one location has to be the same as the amount flowing around in any other location. So instead of calling it I1, I2, and I3, I'm simply going to recognize that I1 is equal to I2, and that's equal to I3, and I'm just going to call it the general I to represent the current at any point in this circuit. The last thing that I can do is I can use Ohm's law at each location separately. So at the first resistor, for example, I can recognize that V1 is the same as the current times the 5 ohm resistor that I have at that location. In the second spot, it will be the current times the 10 ohm resistor. And finally, in the third spot, again the current, but this time it's going through a 15 ohm resistor. What that does is it gets me an expression for V1, V2, and V3 in terms of one common variable that I can solve for. So here my 9 volts will be equal to I times a resistance of 5 ohms plus I times a resistance of 10 ohms plus I times a resistance of 15 ohms. The expression for V1, V2, and V3 respectively. So this is like 5 I's, this is like 10 I's, and this is like 15 I's. So if I have a common variable, then I can collect like terms. This is like saying I have 5 iguanas, 10 iguanas, and 15 iguanas. So that means I have a total of 30 iguanas. 5 plus 10 is 15, plus the other 15 is 30 I's. And now I can divide both sides by 30 ohms. And I can recognize then that my current is going to be, I think it's 0.3, yeah, 0.3 amps. So that means my current at any point in this circuit is going to work out to the same value, 0.3 amps. Now I can use that in my individual expressions for V1, V2, and V3 to find the voltages at all of the different locations. So for 1, V1 was equal to I times 5 ohms, so 0.3 amps times my 5 ohms for a voltage of 1.5 volts. At 2, my voltage is equal to my current times 10 ohms, so 0.3 amps times the 10 ohm resistor at that location for 3 volts. And finally at location 3, V3 is the current times the 15 ohm resistor, which would be my 0.3 amps times 15 ohms and a voltage of 4.5 volts. I can check that this satisfies my Kirchoff's law by recognizing that 1.5 plus 3 plus 4.5 adds up to 9, which was the total voltage on my battery in the first place. So I found the voltage at each one of these resistors, the current at each one of these resistors, and so you can say that I have solved this electrical circuit. So that's how you exploit the common current in a series circuit to solve a series circuit.